Hello guys, welcome to a new video. My name is Chintan Bara and I am from DAIICT and I am doing my project upon discrete mathematics. It is inspired by Manish Kumar Gupta, Professor Manoj Raut and Professor Prosenjit Kun. This is my ID and you already know about our project which is on algorithms of Google Maps. So let's get started with this. But before we get started, do check out the previous videos because if you don't watch them, you won't be able to understand what is happening or what's going on here. So let's get started. My topic is problems related to Dijkstra'S algorithm. So basically, I'm trying to show that what kind of problems can occur on the practical ground in Dijkstra'S algorithm. As you know, already know about Dijkstra'S algorithm very much, I guess, from the previous videos. So a few problems can occur on the practical ground only. Theoretically, it's not much of a defective. So first one is inability to handle negative weights. In this algorithm, we assume that all edges are non-negative. If any of them were to be negative weighted, then the algorithm might consider it as a lower value and it might result in incorrect output. Next up is inefficient for large graph. This algorithm traverses through node and one node to another node. So you can understand that it has a time complexity of big O of v plus e times log v, where v is the number of vertices and e is the number of edges. Hence, if it traverses from node to node, then for larger graph, the it might get more inefficient. Next up is inability to handle disconnected graphs. If the graph is disconnected, meaning that if there is any vertices or nodes that are not reachable from the source node, let's say that certain nodes are not connected to each other through edges and that node only has the shortest path, then in that case the algorithm might produce an invalid short path. Up next is inability to handle graph with cycles. Now think of a graph that has four nodes connected to each other and one of the node is connected to source node and another node is connected to the destination. Now the source node which is connected to that cyclic loop of four nodes is has started traversing. Now the algorithm might get stuck into that four node which are connected cyclically because of the equal distances, or you can take any formation which results in equal edges, equal weight of the edges, and the algorithm might generate an incorrect output or it might get stuck into the loop for infinity. Such graphs are called DAGs. This is written here, directed acyclic graph. Okay, so next up is sensitivity to edge weights. Now Dijkstra'S algorithm assumes that the edge weights are static and do not change during computation. If the edge weight change dynamically during the algorithm's execution, it might produce invalid result. So you already saw through example that weights cannot change uh, as per Dijkstra'S algorithm, and if they change, which is think of a case scenario that you are traveling and you change your destination node from one place to another, then in that case the Dijkstra'S algorithm might get confused with the destination node and result in an improper shortest path. Which might result in an improper shortest path. Up next is inefficient updates of priority. Now, Dijkstra's algorithm normally uses a priority queue to keep track of the nodes with their respected distances. And if you are a coder, you know about priority queue very much. But to give it a short, view of information, a priority queue is something that prioritizes certain things and certain values. So, Dijkstra's algorithm normally uses a priority queue to keep track of the distances, the shortest node path as well as the distances. And this priority queue, while updating, uses a lot of time as well as space. So if the graph which we are traversing with is larger, much larger in fact, then it might get worse in that case, because updating the priority queue is not an easy task. Now to counteract some of the inefficiencies of Dijkstra algorithm, Bellman-Ford algorithm was introduced. There is also the A-star algorithm, which you might, if you want to understand, or you should understand by watching our videos, by watching next parts of our video. This is only just a little discussion about Bellman-Ford algorithm, which is kind of a replacement for the Dijkstra's algorithm. Now, Bellman-Ford algorithm is also a graph traversal algorithm, which is used to find the shortest path between particular source node and all other nodes in the weighted graph. The most beneficial feature of Bellman-Ford is that it can handle negative weight edges, unlike Dijkstra's algorithm. Now let us look at the steps of Bellman-Ford. Pretty much alike to Dijkstra's algorithm, but it has some sense of where to change or where to fall apart, where it can fall apart. Uh, Initializing the distance of every vertex to be infinity, except source node set to zero. Uh, Repeating now. There is a process which has to be repeated n minus 1 times during the during this whole scenario, where this n minus 1 times is n, where n is particularly the total number of nodes in the graph given. So the process is, for each edge group xy in the graph where x is the source node and y is the destination node, we keep relaxing the edges by updating the destination as we find the shortest path to that node. So basically, while traversing, you need to update the edges to the shortest path you can find, and thus by traversing in only one particular direction, it becomes more efficient. It is calculated simply by finding the minimum of the current distance and the distance to you plus the weight of the edge. Now here, up to this point, this is as perfect as this algorithm. But what if there is a negative weight included in the graph? So Bellman-Ford algorithm uses one more method, which is to traverse the whole graph and iterate itself once more to see if there are any negative weights in the graph, and if there are any negative weights, using them to find any shorter path if possible. This algorithm has a time complexity of big O of v times e, where v stands for the number of nodes and e is the number of edges in the graph, and it contains a space complexity of big O of v for storing the distance array. So thank you guys for listening up to me up to this point. Do check out our other videos to understand more about the A-star algorithm, particularly because we haven't yet understood anything about A-star algorithm, I suppose. And you already know about Dijkstra algorithm. So like the video, and thank you.